So we're looking here at the disorders of the water balance. The first major disorder of water balance is going to be dehydration. In dehydration, as we have stated earlier, the water intake is far less than the water output. This might be triggered by hemorrhage, might be due to severe burns, prolonged vomiting or diarrhea, profuse sweating, water deprivation, diuretic abuse. All those can trigger a negative fluid balance or dehydration. So the output here is far greater than the intake. So what happens in this case? If I have excessive water loss from the extracellular fluid compartment, the solutes here gonna create a higher osmotic pressure. Remember, if I keep losing water, the solute concentration gonna be rising in the extracellular fluid, and this includes plasma and interstitial fluid. And as a result, what happens? This high solute concentration in the extracellular fluid compartment is going to be pulling the water out by osmosis from the cells. This will cause the cells to lose water and to shrink. And as a result of this, patients will develop symptoms of like thirst, dry, flushed skin. Why dry? Why skin here is going to be dry? Because the same concept, like the salivary glands, the sweat glands are getting the sweat from the blood vessels. So if I have high concentration of solutes in my blood vessels, the sweat glands will fail to pull water out, and as a result, I'm not able to release sweat. Why flushed skin? Why the skin is going to be flushed in case of dehydration? Because another way by which your body going to be responding to an increase in its body temperature is by dilating its peripheral vessels, performing a vasodilation of the peripheral vessels, which will allow the body to lose heat by radiation. So I'm radiating the extra heat to keep my body temperature at a normal level. So here, the dilation of the blood vessels of the skin is what causes the flushed skin. Patients will first show weight loss, fever, mental confusion. It might progress to a hypovolemic shock where I don't have enough blood volume to circulate and to deliver the nutrients and oxygen to my tissues. And can also result in loss of electrolytes. Moving on to another water imbalance, it's the hypotonic hydration or cellular overhydration or water intoxication. So remember this first day of the gym. You changed your life, you decided to change your life, you're going to be losing all the extra pounds, you got a new gym membership, and this very first day in the gym, what you're going to be doing, you're going to be running, you're going to be exercising, and you keep drinking water. What happens by the end of the day, of this very first day of the gym? You feel you've got nausea, you've got muscle cramps, you have headache, and for many of us, this would be the first and last day of the gym. And your gym membership is like a donation to the gym, maybe. So you never go back to the gym. Did this happen to any of you? Yes. Yeah, so I'm not the only one. So why this happens? Why would I have nausea? Why would I have vomiting? I will have muscle cramps? Why would I develop headaches? What did I do wrong? The problem here is that I ingested lots of pure water, just pure water. So I keep adding water to my extracellular fluid compartment. And as a result, what's going to happen to the solid concentration? If I kept adding water to the extracellular fluid, the amount of solutes, it's the same, but as I add to it more water, its concentration gonna be dropping. So now I have a drop in my extracellular fluid osmolarity. Compared to my cells, I have a much higher solid concentration. So what's gonna happen? Water starts to move from my extracellular fluid to the inside of my cells, causing my cells to swell. So I have the mucosal lining of the gastrointestinal tract is going to be swelling. So I will have nausea. In some cases, vomiting. My muscle cells going to be swelling. I have muscle cramps. Other than the regular muscle fatigue, I also develop muscle cramps. Brain cells and meningeal cells, the membranes around the cells, around the brain, gonna be swelling, so I develop headaches. All right. In very severe cases, which is more likely to be related to kidney failure, it might progress to cerebral edema, where the fluid gonna be accumulating around the brain cells that will trigger convulsions, coma, and in some cases might cause death. So too much water is not something good. Too much water is not something good. So what am I supposed to do instead? To not go to the gym in the first place? No, go to the gym, but try to get not just pure water, try to drink Gatorade, exactly. Something that has the same solid concentration as your cells for you to not have a major drop in the extracellular fluid osmolarity. All right. So is sweating more than other people is normal? So it's all according to the body temperature. So there may be some innervation. So that might be exaggerated in some, where I've got excessive sweating in the palms and soles than normal. This might be something, but excessive sweat, if I have really higher metabolic activity, so my body heats up faster, this might cause me to sweat more profusely compared to others. Also, if I'm drinking enough more water than another person, my tendency to sweat is going to be much higher than the other person, because you see how your body is going to be responding to low water intake. It's going to be preventing you from sweating. Tries to find a different way to reduce your body temperature. So many factors here: body temperature, innervation, and the activity of the autonomic nervous system. Another factor is going to be the water intake itself. All right, so all those can be contributing factors that will cause the variation in the amount of sweat that a person can have. Although two people might be performing the same exact exercise, one is going to be sweating more than the other. It's according to his body weight, his metabolic activity, and many other factors. All right. All right. So our first in classic activity question for today is going to be, what other names that we give for overhydration? What other names that we give for overhydration? Which ones do you think? So overhydration is also called hypotonic hydration and water intoxication. So again, overhydration is hypotonic hydration and water intoxication. So the good answer here is going to be both C and D, which is F. All right, is this clear? Is this clear? So other names for cellular overhydration is both hypotonic hydration and water intoxication. So it's not always drinking large amounts of water is going to be something good, right? Drinking too much water can cause intoxication. Electrolyte balance. Electrolytes are the salts, acids, and bases. Electrolyte balance usually refers only to the salt balance, and it's going to be regulated by the kidneys. Why do we need to maintain normal concentration of electrolytes of salts inside the extracellular fluid? First thing is to control the fluid movement. We've seen if I have higher osmolarity on one side of the membrane, it's going to be putting water. So in order for me to regulate the water movement across the membrane, like what we've seen also when we did perform the reabsorption, remember 60% of the water that we reabsorb is going to be reabsorbed following the sodium in the proximal convoluted tubules. So the sodium reabsorption did allow the water movement. So if I didn't have sodium present, I wouldn't have been able to absorb this water back to my blood. So control fluid movement is going to be one of the major importances of salts. Neuromuscular excitability. If you remember, in order for a muscle cell or a nerve cell to depolarize, it did allow sodium in, and in order for it to repolarize, it allowed potassium out. In the cardiac muscle cells, remember, I have extended the repolarization phase by allowing calcium influx. I'm allowing the calcium in while I'm losing potassium to the outside. So remember this here, you needed lots of salts to allow normal excitation of the nerves and muscles. Secretory activity is also going to be regulated by salts, like the influx of calcium to trigger the release of hormones from the endocrine glands, and to determine the membrane permeability. For example, if you want to allow the reabsorption of something like glucose in the proximal convoluted tubules, if you remember from last meeting, I allowed the glucose reabsorption to take place in the proximal convoluted tubules by co-transport with sodium. So if I didn't have the sodium, I wouldn't have been able to reabsorb the glucose in the same time. So here, the membrane is permeable for the glucose because of the presence of the sodium. If I didn't have sodium, I wouldn't have been able to allow the glucose back into my blood. The sodium is the major cation of the extracellular fluid compartment. It plays the largest bulk of the osmotic pressure, and as a result, it controls the water volume and distribution between the different compartments. It contributes alone by 280 milliosmol compared to the total osmolarity of the extracellular fluid is going to be 300 milliosmol. So more than 90%. More than 90%, might be higher than this. Okay. It's going to be 93.3. So more than 90% of the total extracellular fluid osmolarity is going to be contributed by just the sodium. Sodium content may change, but its concentration can't change. Can you explain this for me? What do you understand from this statement? I can change the sodium content, the amount of sodium, but its concentration gonna remain constant. What this means? How do you explain it? What do you think? I can add more sodium, but its concentration will not change. How do you explain this? By one word. Osmosis. Remember, sodium pulls water. So if you added sodium, it pulls water, so its concentration gonna remain the same. So let's say on here, if I have each sodium is gonna be putting one water. So if I have a can containing 5 sodium, this means that those 5 sodium are accompanied by 5 water. So when I add 1 sodium, I did change the content. Now I have 6 sodium. But what happens when I add the sodium, it pulls with it water. So now instead of having 6 sodium, I have 6, instead of having 5 sodium, I have 6 sodium, but the concentration didn't change because simply this sodium that I did move in, it's going to be putting water. So it's 6 over 6. So it's going to be the same exact concentration. Does this make sense? So you can't change the sodium content. You can add sodium, but it's going to be always putting water, so its concentration can't change. It's going to remain the same. How do I regulate the sodium balance? Aldosterone promotes sodium reabsorption, and the sodium reabsorption here under the effect of aldosterone, if you remember, it's going to be taking place in the distal convoluted tubules and on a very limited basis in the collecting ducts. the amount of sodium that I can reabsorb under the effect of aldosterone is only 10% of the sodium that gets filtered. So if I'm following here, the sodium, proximal convoluted tubules, loop of Henle, distal, and collecting ducts. All right. So if I told you I filtered, let's say, 10 sodium out from the blood, around 6 sodium gonna be reabsorbed back in the proximal convoluted tubules. This is not regulated by the aldosterone. This is a mandatory reabsorption. I have to get those back. 60% of the sodium gonna be moving back. So if I say here 100 sodium got filtered, so it's gonna be 65%. 65 of those sodium gonna be reabsorbed back in the proximal convoluted tubules. The remaining gonna be splitted to get reabsorbed in the remaining parts of the kidney tubules. 25% gonna be reabsorbed back in the ascending limb of the loop of Henle. Remember, the descending limb didn't allow sodium reabsorption. It allowed free water reabsorption, just free water. I was formed by simple squamous epithelium. Only water gonna be traveling here. Free water reabsorption. But the ascending limb is gonna be pulling 25% of the sodium that got filtered back. So here, if I filtered 100 sodium, 65 of them got reabsorbed in the proximal convoluted tubules, and 25 gonna be reabsorbed in the ascending limb of the loop of Henle. So how many sodium are still remaining out of those 100? I did reabsorb 65, I did reabsorb 25. How many of them are still gonna remain in my filtrate to reach the distal convoluted tubules? 100 minus 65 and 25, you still have 10%. 10 of the sodium gonna still be in the distal convoluted tubules. This is the optional part here. If I want to increase the blood pressure, if I want to increase the blood pressure, what would I do? I will pull this 10% of the sodium back to my blood. And who will do this for you is the aldosterone. You remember where did I release the aldosterone from? You remember from last class? It's released from the adrenal cortex. And remember what triggered the release of the aldosterone from the adrenal cortex was the angiotensin II. So angiotensin II that got formed due to a drop in the blood pressure will do what? Will activate the adrenal cortex to release aldosterone, and the aldosterone will do what here to the sodium? Is going to be pulling the remaining 10% of the sodium back to my blood. This is only in case of low blood pressure. But what if I have a normal blood pressure or a higher blood pressure? You wouldn't be forming angiotensin II because you have normal blood pressure, so the renin will not be released, and if you're not releasing renin, you will not be converting angiotensinogen into angiotensin 1, so you don't have angiotensin 2. And if you don't have angiotensin 2, there is nothing that will trigger the release of aldosterone from the adrenal cortex. So you don't have the aldosterone, so you're gonna be not reabsorbing this 10% of the sodium, and this sodium followed with its water gonna be released out in the urine. So what is the mandatory sodium reabsorption? It's 90%. Aldosterone only controls what percent of the sodium? Only 10%. And aldosterone is going to be only present if I do have low blood pressure, because what is actually going to be triggering its release, it's the angiotensin 2 that gets formed in case of low blood pressure. Does this make sense? Questions? So again, a repetition of what we've previously discussed. The renin-angiotensin mechanism is the main trigger for the aldosterone release. Remember, if I have low blood pressure, the granular cells of the juxtaglomerular apparatus gonna be activated and they will start to release renin. Remember, renin gonna do what in here? Gonna be converting the angiotensinogen into angiotensin 1 that will then be converted into angiotensin 2, which triggers the release of aldosterone. Aldosterone brings about its effects slowly. It takes hours to days, and this explains why angiotensin 2 has many mechanisms of action, because some of them, like the aldosterone action here, is going to be much slower to have a major effect in terms of my blood pressure. Moving on to another hormone that will also regulate the sodium balance, which is ANP, or atrial natriuretic peptide. Atrial natriuretic peptide, from its name, what can you understand? I am a peptide, means what? Means I have a protein nature, I'm full of amino acids. What else can you understand from just the name, ANP? What else can you understand from the name? Do you understand anything from the name other than it's a peptide? Yeah, it's going to be released from where? From the heart. To be more specific, from the atrium of the heart, right? Can you remind me what is meant by diuretic? What's a diuretic means? Water loss in the urine. Water loss in the urine. So what is meant by natriuretic? So diuretic is water loss in the urine. What is natriuretic? So uretic means loss in the urine. What is natrio? Do you know what is the name of the element that I put the atomic symbol for on here? What is this? C. What is the element? Carbon, right? H. Hydrogen. Li. Lithium. How about Na? What's Na? Sodium, right? So why is the atomic symbol? Why is the atomic symbol on here? It's not the first letter or two letters of the sodium. Also, it was the first letter in carbon. It was the first letter in hydrogen. Because we didn't give those atomic symbols according to the English name. We give them according to the Latin name of the element. So what is the Latin name for sodium? It's natrium. So natrium is sodium. So what can you understand now just from the name? Just by looking at the name here of this hormone. Atrial natriuretic peptide. So it is a hormone that is a peptide, a protein in nature. It's released from the heart and it causes the sodium loss in the urine. This is what the name tells me, atrial natriuretic peptide. So if it allows you to lose sodium in the urine and it's released from the heart, what do you think gonna be triggering its release? And what's gonna be its effect on the blood pressure? What is the effect on the blood pressure, as you said, Rachel? What's gonna be the effect if I'm losing the sodium out in the urine? What's gonna be the effect on the blood pressure of this hormone? It's gonna be reducing my blood pressure. And if you remember, who hates high blood pressure? It was the heart who hates the blood pressure, high blood pressure, because it's gonna be the afterload. So that it needs to overcome every time it ejects blood out. So it makes perfect sense that the triggering factor, what triggers the release of the atrial natriuretic peptide, it's an increase in the blood pressure. And it's definitely going to be acting to do what to the blood pressure? To reduce the blood pressure. So it's so logical. So all this information, I can't just guess from the name. Just the name told me all this. All right, it is so logical. So how the heart gonna detect that you've got a high blood pressure? This is my heart like this. In my right atrium, right ventricle, left atrium and left ventricle. And this is the how the heart will know that you've got higher than normal blood pressure. Unlike what most of you will think, that the aorta here has high blood pressure, so the heart gonna be detecting. But remember, you don't have access to the pressure in the aorta here because the valves will close if the blood gonna be returning. What do you have access to is the venous return. If I have an increase in the venous returns, this means that I have higher blood pressure in my systemic circulation. If I have high pressure, this means the blood keeps flowing and returns back to the heart at a higher pressure, increasing the amount of blood that is coming back to the heart. So your heart detects the increase in the blood pressure not by direct detection of the pressure in the arteries, but by detecting the amount of venous return. If I get more venous returns, this means for me that I have a high blood pressure. And how would you detect that you've got an increase in the venous return? By detecting the degree of stretch applied to the wall of the atrium. So when I have an increase in the stretch of the wall of the atrium, this means I have high blood pressure. This means I have high blood pressure. This is how your heart will detect that you've got a high blood pressure. So how would it respond? It responds by releasing this hormone, atrial natriuretic peptide. Atrial natriuretic peptide has 3 target organs. But keep in mind, keep it in the back of your mind that ANP is trying to reduce the blood pressure. First target organ for the atrial natriuretic peptide is going to be the juxtaglomerular apparatus, the granular cells. Remember, granular cells were detecting an increase in the blood, a reduction in the blood pressure, and this reduction did cause the granular cells to release renin, which triggered the activation of angiotensinogen into angiotensin 1 and so on. So ANP is going to be doing what here to the juxtaglomerular apparatus? It's going to be inhibiting the granular cells from releasing renin. And if I don't have renin, what's going to happen to the levels of angiotensin 2? If I don't have renin, would I have angiotensin 2 available? What do you think? No. Remember, renin is required for you to get angiotensin 2. If you don't release renin, you don't get angiotensin 2. And can you remind me, please, what was the very first action of angiotensin 2 that we mentioned? We mentioned 5 actions for angiotensin 2. The very first one, it was from its name, angio blood vessels and tension. So what was the very first action here for angiotensin? It's called angio blood vessel, tensin, applying tension. So what is the very first action of angiotensin 2 that we mentioned? It's called the guy who applies tension on the angio, on the vessels. So what was the first action? Constricts arterioles. Vasoconstriction. So if I don't have the guy who constricts the vessels, what's going to happen to my blood vessels? To the arterioles? If I don't have angiotensin 2 to constrict, what would they do? Would they constrict or dilate? Anything in your body is a balance. So if you don't constrict, what's going to happen? If I don't have angiotensin 2, I'm not able to constrict. So what's going to happen to my arteries? My arterioles, they will dilate. We'll have vasodilation. And if you remember back in the heart and vascular system, mean arterial pressure was affected by three factors, which are my cardiac output, total peripheral resistance, and blood volume. So when you dilate the arterioles, what's going to happen here? You're going to have a drop in your total peripheral resistance. Remember, dilated arterioles going to apply less resistance, and less resistance going to result in what? In terms of blood pressure, decrease in the blood pressure. So when I dilate the arterioles, this is going to result in a drop in my blood pressure. And this is what I want. I did have high blood pressures that triggered all this to take place. And my main purpose here for A&P will be to lower down this high blood pressure to normal. The second target organ for A&P will be the hypothalamus. Remember, the hypothalamus was releasing a hormone through the posterior pituitary gland called ADH, anti-diuretic hormone. And if you remember, as we mentioned many times today, what was the action here for ADH? It retains water. So the effect here of A&P will be to inhibit the release of ADH. If I don't have ADH, what's going to happen to the water that I will be retaining under the effect of ADH? Would I still retain it, or will it be released out in the urine? Would I still retain this water if I don't have ADH, or will it be released out in the urine? What do you think? Released out. No water retention. So what happens to my blood volume? If I'm not retaining this water, it keeps moving out in the urine. What happens to my blood volume? Will it increase or decrease? What do you think? If you lose the water out, blood volume decreases. And if the blood volume decreases, what's going to happen as a result of your blood pressure? It decreases. And this is what you want. A third target organ for A&P will be the adrenal cortex. And if you remember, adrenal cortex was releasing a hormone called aldosterone. And the aldosterone was responsible to do what? If you remember, we mentioned it a few minutes ago, sodium reabsorption. So A&P will do what here? It's going to be inhibiting the release of aldosterone from my adrenal cortex. If I don't have aldosterone, would I be reabsorbing? Do you remember what percent of the sodium gets reabsorbed under the effect of aldosterone? What percent of the sodium gets reabsorbed? What percent was this? 10%, right? So here, if I don't have aldosterone, what's going to happen to this 10% of the sodium that got filtered? It's going to be released out in the urine. And is the sodium going to be moving alone, or it's going to be followed by water? What do you think? Can you change the concentration of the sodium? Yes or no? No, you can't. Why? Because sodium, whenever it moves, it pulls water. So you're going to get rid of this sodium and you're going to get rid of this water out in the urine. So what happens to my blood volume as a result? If I'm losing this sodium and water out, what happens to my blood volume? Blood volume going to decrease. And as a result, what's going to happen to my blood pressure? It decreases. And this is what you want. You are actually released from the heart to reduce the blood pressure. This is again what hormones that we are talking about here, atrial natriuretic peptide. And you see here, this sodium that got released out in the urine is the reason why it's called atrial natriuretic peptide. Because we find out that whenever this peptide is present in the blood, sodium gets released out in the urine. So we called it atrial natriuretic peptide. All right. Questions? All right, so looking here, what triggered the release of ANP is the increase in the stretch of the wall of the atria. And why would I have an increase in the stretch in the wall of the atria? Due to an increase in the venous return resulting from high blood pressure. Atrial natriuretic peptide, when it's released, it targets juxtaglomerular apparatus that causes the reduction in the renal release. And if I don't have renin, I won't have angiotensin II that constricts the blood vessels. So in the absence of angiotensin II, this is going to result in a dilation of the vessels. Reduction in the total peripheral resistance is what causes the decline in the blood pressure. Looking on here, as the second target organ for atrial natriuretic peptide is going to be my hypothalamus and posterior pituitary gland. ANP is going to be inhibiting the release of ADH. When I inhibit the release of ADH, there will be water loss in the urine. This is going to cause a drop in my blood volume and so a drop in my blood pressure. The third target organ for ANP will be the adrenal cortex. Now remember, once I get a atrial natriuretic peptide as the adrenal cortex, this is going to be inhibiting the release of aldosterone, which normally is responsible to reabsorb the sodium. So if I don't have it, I will not be reabsorbing the sodium and water, and this water is going to be lost out in the urine. This is going to cause a drop in my blood volume and so my blood pressure. Questions? All right, so this here is going to be the second half of your essay question. In the upcoming lab exam. Remember, we have one essay question that has two parts. How your body responds to an increase in the blood pressure. This is going to be your response. I've detected a stretch in the atrium, causing this stretch is caused by the increase in the blood pressure. Atria will be releasing ANP, and those will be targeting three target organs. and you're going to be explaining the effect of the ANP on each of them and how this effect is going to be causing a decrease in the blood pressure. How your body responds to a drop in your blood pressure. This is what we discussed last session. And you need to remember, we need to mention the structure of the juxtaglomerular apparatus, the function of the granular cells, and that they are acting as mechanoreceptors and they will be releasing renin when they detect a decrease in the degree of stretch of the afferent arteriole. We're going to mention how renin going to be activating angiotensinogen into angiotensin 1, then gets activated by angiotensin converting enzyme to angiotensin 2. Remember the 5 different functions of angiotensin 2, those are highly important. Quick reminder, vasoconstriction of the arterioles, causing an increase in the total peripheral resistance and so pressure, sodium reabsorption, direct action of angiotensin 2 and indirect action by enhancing the release of aldosterone from the adrenal cortex. Third action of angiotensin 2 will be by acting on the hypothalamic thirst center and activation of the hypothalamus to release ADH. The function number 4 for angiotensin 2, by which it increases the blood pressure, will be the constriction of the efferent arteriole, which will cause the decrease in the hydrostatic pressure of the peritubular capillaries that result in more reabsorption. The last function that we have discussed for angiotensin 2 was the contraction of the extraglomerular mesangial cells. And remember, the contraction of the extraglomerular mesangial cells will result in a decrease in the surface area available for filtration. And if you don't have enough surface area to allow the filtration to take place, this means you would have a reduction in the amount of water that gets lost out in the urine. All right, so those are simply speaking the 2 parts of the essay question: how your body responds to high blood pressure, how your body responds to low blood pressure. Again, this question is going to be out of 15 points towards your lab exam. Questions? Any questions? All right, so this completes our discussion for today. Please write your name in the chatting box, first and last name, before you leave. And if you've got any specific question related to the exam or related to how to study, please ask me in the chatting box for me to respond before we leave. All right, for the rest of you, yes, only one question today. Only one multiple choice question today. All right, Rebecca, no problem. For Ms. Muhammad, let me double check the email. For if you've missed any previous lecture or part of a class or part of a lecture, so I will be sending. I believe I've sent this before, but let me pull up the link for the YouTube channels that I'm using to upload those recordings. All right, so I I upload them. I upload them during the weekend. All right, so expect the last class meeting to be uploaded on this YouTube channel this weekend. All right, Ms. Muhammad. ANP is an accepted abbreviation. For Maritza, ANP is an accepted abbreviation for natriuretic peptide. But 82, 81, it's not like a scientific abbreviation for angiotensin 1 and angiotensin 2. But ANP is an accepted abbreviation for natriuretic peptide. And ADH is an accepted abbreviation, but not angiotensin 2 and 1, 81 and 82, they are not accepted abbreviations for angiotensin 1 and angiotensin 2. So how your body responds for Christian, how your body responds in case of low blood pressure, you're going to be explaining the structure of juxtaglomerular apparatus, granular cells, how the granular cells going to be detecting that there is a drop in the blood pressure. They will be releasing renin in response, which will be converting so and so to get angiotensin 2, and then you're going to be stating the different actions of angiotensin 2 on how angiotensin 2 going to be increasing the blood pressure. This is the first half of the question. Second half of the question is how your body going to be responding to a state of high blood pressure. So if I have high blood pressure, what would I do? This is what we just mentioned today. If I have high blood pressure, this is going to cause stretch of the atrium, and ANP going to be released. ANP targets 3 organs, and you're going to explain how ANP, when target each of those organs, going to cause the reduction in the blood pressure back to normal. So